this thing called virtual memory. So hopefully for those that's astute, you now understood that paging is actually quite a cool thing. If we can break up a process into smaller chunks and we start looking at the logical addresses of a process and we disconnect that from the physical addresses of a process, then we can do quite a lot of things in it. But up to this point, the assumption was that when we load a process, whether it's effectively, let's say our process consists of 5-page frames, those 5-page frames must be in memory. Right? We're going to take attendance. Right. Now with virtual memory helps us to take that even further. And it allows us to effectively distinguish processes that's potentially too big to fit into our physical memory. And the reason why we can do that is because even though we've got a lot of addresses available for us, realistically speaking, any process that we run, not all of its code has to be in memory at the same time. Right, that's one of the things. So, code needs to be in memory to be executable, but the entire program is rarely used. There are certain things that we don't always have, like error code, unusual routines, large data structures. The entire program code is not needed at the same time as well, and we've got considerable ability to execute partially loaded programs. The program no longer is constrained by the limit of physical memory. Each program takes less memory while running, and it's less I/O needed to load or swap programs into memory. Each user program runs faster. So what does virtual memory allow us to do? This to form, for example. The nice thing about virtual memory, meaning we separate the user logic from the physical memory, is that first, only part of the program needs to be in memory for execution. So if we consider an application, and we say our application has, let's say, 1,000 kilobytes of actual code, but we've got a lot of memory addresses, we only really need a portion of that code in the actual RAM of the computer. The rest of the code that we're not going to use can be on what we call the vacuum store, meaning on the hardware. Logical address spaces can therefore be much larger than physical address spaces. Of interest sake, your average computer today has about, I would say, 8 gigabytes of RAM, maybe 16 gigabytes of RAM. The 64-bit architecture that we have inside our computers today can expand it to allow the 64-bit memory address space. Now, if you actually calculate, that is a nearly swear, huge amount of memory addresses that's available for your computer. But there's no way that you will, probably in the next 10 years, will have memory that's that big. Highly unlikely. And that allows us to have these big logical address spaces with stacks that can grow really big, with heaps that can grow really big, and there's no problem. You can always really have nice, large applications being able to run, but realistically, we only use a small portion of that in physical memory. It allows address spaces to be shared by several processes as well. It allows for more efficient process creation. You'll see now when we start loading a process that you don't always have to load the whole process into your RAM of your computer. More programs can potentially run concurrently because of this. We don't have to have everything inside the memory, and then also less I/O is needed to load or swap our process. So these are a number of the advantages that we have with virtual memory. This is important. So effectively a virtual address space, or the logical address space, is the logical view of how the process is stored in memory. It usually starts at address 0, and then we've got a contiguous address until the end of space, on the end of the space. In your 32-bit applications that you guys have been writing so far in your assembly, you've got from 0 to 4 gigabytes. Well, not strictly speaking, because part of that is what they call kernel memory. So typically, the lower half is what we have available for our user programs. But as I said, on the 64-bit, we've got this huge amount of address space that's available. But the physical memory is organized into the page frames like we had. The memory management unit is still involved here to help with the mapping of the page frames. And we typically implement virtual memory into what they call demand paging or demand segmentation. Demand paging is actually the more common way of doing it, but segmentation is also available if necessary. Segmentation is where we physically break up our process into units. It's typically bigger than a page, and you can swap these units into and out of memory, exactly like we covered in the previous chapter. So here's a nice example of logically how it looks like. So we've got on the left-hand side, it describes this huge virtual address space or logical address space up to page very, very much. That's what the D basically means. It's a huge number of pages. Again, we've got this thing called a memory map that is represented typically by a page table. The page table then describes whether a specific page is currently inside the physical memory or whether it's in the backup store. And that's what's nice about it. So in chapter 7, we said that pages have to be in physical memory for a specific process. Here, no. You can have some of the pages be in the backup store, some of the pages in main memory. Only when you need to run that specific address or the code, when you access the data that's inside that memory, does it need to be in the physical memory of the computer. If it's not in the physical memory of the computer, then from the back-end store, it will take that page, load it into the main memory, and potentially also make space available by paging some page frame away onto the disk. So here's a nice example of the virtual address space. Again, typically your process breaks up into these different areas. We've talked about this before, where you've got the code section, data, the heap that can grow upwards, and the stack that can grow downwards. But the nice thing about these virtual address spaces is that we can maximize our address space now. We can really have big ones. Unused address space between the two is a hole that is very big, but we can effectively make use of it. No physical memory is needed for this hole or the stack. That's great for us to know that we can still have processes that will fit in. It enables for sparse address spaces with holes that can grow. System libraries are shared via mapping. So again, we go to different libraries. Shared memory is by mapping pages can either be right into a virtual address space or not, and you can potentially also, if you've got multiple processes that forks, meaning when you've got created a duplicate of it, it can also speed up process creation. Here's just an example of how multiple processes using shared pages can actually access shared libraries. This was hinted at already in the previous chapter. Okay, then tomorrow we will continue with what's called